Okay, we're continuing with Chapter 2 in the Algebra playlist. In this video, we're going to go through the fourth section, which is on linear functions and linear equations. So in this section, we're going to take a look at our first function, our first official function, the linear function. Okay, now, but let's first make sure we understand the different categories that we're putting expressions and equations into. So in pre-algebra, we talked about different categories that expressions are put into, you know, like a polynomial expression, a rational expression, radical expression, absolute value. And the categories that we put equations and inequalities into were based on the types of expressions or terms in the equation or inequality. Okay, but we're also going to be putting equations and the corresponding expressions in the equations into more categories based on the specific type of graph that equation produces. So we saw an example of this with the equation of a circle. Now, we can note, though, that, so if we write out the general form of the equation of a circle, okay, so this is the equation of a circle in the variables x and y in two variables. And that's one category that you put this equation in, but this is also a quadratic equation in x and y. So this is polynomial for sure. All of the exponents and the variables are whole numbers. But then the term with the largest degree is degree 2. We have degree 2 terms and 3 linear terms here. So this is a quadratic equation in x and y, as well as an equation of a circle. Now, this is a subcategory of quadratic equations because if we put more constants here, like this could be a constant d, this could be a constant e, this is still a quadratic equation in x and y, but now we wouldn't, if these coefficients are on 1, we don't have the equation of a circle. Okay, so you can see the different categories that we put equations and expressions into. Now, but the equation of a circle was not a function of y and x or x and y. So in this section, we're going to study our first function, the linear function. Okay, so we know from chapter 1 that a linear equation in any number of variables is an equation to where the expression on both sides of the equation is a linear expression. And we know that a linear expression is a subcategory of polynomial expressions. A polynomial expression is where every variable in the entire expression is raised to a whole number exponent, 0, 1, 2, 3, 4. But a linear expression is a subcategory of polynomial expressions to where the total degree of each term in the expression is 1 or 0. So this is a linear term. This is a linear term. This is a linear term. This is just a constant. So if every single term in an equation is a linear term, then you have a linear equation. Okay, and so this definition here talks about a linear equation in two variables, and they write out this all-encompassing form here where they say, okay, a linear equation in two variables in complete general, you can think about as being a constant times x plus a constant times y is equal to a constant. And as long as both a and b aren't 0 at the same time, otherwise you don't have an equation in any number of variables, then this covers all of the possible cases of having a linear equation in two variables. And we can extend this to any number of variables. This would be the general form for a linear equation in 4 variables, right? Now, but focusing on the linear equation in 2 variables at the moment, you can see that this definition here says that this ax plus by is equal to c is called the standard form of an equation of a line. And what they're talking about here is it's the same idea for how we had the standard form for the equation of a circle. This equation here is representative of any circle of any radius at any center location that you could possibly draw in the Cartesian plane. Well, that's exactly what this is. This equation is. This is all encompassing in regards to any line you could possibly draw in any orientation in the Cartesian plane. Slanted to the left, slanted to the right, horizontal, vertical, any line. And if we come to the next page, we can see 3 examples of this here. So the equation 2x plus 3y is equal to 6. If we think about ax plus by is equal to c, then in this case, a is equal to 2, b is equal to 3, c is equal to 6. And so to graph this, what they do is they pick an x, solve for y, pick another x, solve for y, pick a y, solve for x, and they get 4 points. And what you find is that if you draw a line through those 4 points, then from there, if you pick any point you want on that line, even if it's not on those original 4 points, and so that point is going to have an xy coordinate, and you plug that xy coordinate into this equation, it's going to be a solution. And so that's the meaning of that. This graph is the graph of this line in the Cartesian plane. Okay, now they then graph this equation here, x is equal to minus 3. Now, how does that relate to this standard form of the equation of a line here? Well, in this case, a is equal to 1, b is equal to 0, c is equal to minus 3. Remember, for this standard form here, a, b, and c can be any real number as long as both a and b aren't 0 at the same time. If that's the case, then you have the equation that represents some line in the Cartesian plane. Now, just note that it's not like you couldn't think about a, b, and c being any complex number, with x and y being variables that could represent any complex number in the complex plane. But in this course, any time we're thinking about graphs of equations or inequalities, points on the graph are going to correspond strictly to real numbers. The idea of graphs involving complex numbers, graphs of equations, inequalities involving complex numbers, is something we'll talk about in a future course in complex analysis. Okay, but now the equation x is equal to minus 3. How would you graph this? Well, okay, remember what a graph of an equation means. You're plotting all of the solutions to the equation. All points that are solutions to the equation, you're plotting on the graph. Well, okay, if we're thinking about what are all of the real numbers that satisfy this equation? Well, it's going to be any point in the plane that has x coordinate negative 3. It doesn't matter what the y coordinate is. The y coordinate doesn't come into play here. If you have an x coordinate of negative 3 with any y coordinate, then you plug that x coordinate in, you get negative 3 is equal to negative 3. So what that means is that this is going to be a vertical line that passes through x is equal to negative 3. All of these points on this line are solutions to this equation. Okay, now if we come to this last equation, 2y is equal to 4. In this case, we've got a being equal to 0, b is equal to 2, c is equal to 4. Okay, what we can do is we can divide both sides by 2 and get y is equal to 2. And now this will make it easier to graph. We can graph this. These two are going to have equivalent solution sets, right? These two equations. So we can graph either one of these. And so y is equal to 2 it's similar to what we did with x is equal to minus 3, except now we've got y is equal to a constant. So in that case, it's going to be any point in the xy plane with y coordinate of 2 is going to be a solution. So in that case, what we can see is that the result is a horizontal line that passes through y is equal to 2. Any point on this line is a solution to the equation 2y is equal to 4. Okay, and so with these 3 examples, what you can see is that this general form for the equation of a line in a plane, in a Cartesian plane, is representative of any line we could possibly draw in any orientation in the plane. Slanted, horizontal, vertical, any line, just like the standard form for the equation of a circle was representative of any circle with any center location and any radius you could draw in anywhere in the Cartesian plane. Now, just note, though, this form here, this form of a linear equation in 2 variables, isn't technically a function yet. Even though when we think about the graph of a line, we tend to think, okay, function, right? It passes the vertical line test in the vast majority of the time. And that is true. However, technically, because this form includes vertical lines, which aren't functions, which don't pass the vertical line test, every other line does pass except for the vertical line. Technically, this isn't a function yet. We haven't turned this into a function yet, even though a line and a plane definitely is way more of a function in general than like a circle is. 99% of the different lines you can draw in the plane are going to be functions, are going to pass the vertical line test. But technically, this like general form for the equation of a line in two variables, or the equation of a line in a plane, isn't a function. Okay, now, something that we want to note is that you would think that if we had a linear equation in three variables, which we know we can graph equations in three variables in a 3D Cartesian coordinate system. Doesn't have to be Cartesian, but let's think about a 3D Cartesian coordinate system, and we're graphing a linear equation in three variables. So something in the form ax plus by plus cz is equal to d. Well, you would think, based on the name and based on the very similar form to the linear equation in two variables, that if we plotted this, we would get a line in 3D. Well, unfortunately, that's not the case, which is kind of confusing. This is actually going to be the graph of a plane. So you'll get the graph something like this. The planes extend infinitely in all directions in the same way that lines do. Okay, and this is similar to how if we extend this standard form of the equation of a circle to three dimensions, so in that case you'd have, it's going to be x minus h squared plus y minus k squared plus, I think it's z minus l squared is equal to r squared. This isn't the equation for a circle in 3D. This is the equation of a sphere in 3D with center location h, k, l, and radius r. And so this is kind of confusing, but the way you can think about it is that in a lot of cases, these equations are going to get their names as far as if they're in relation to the type of graph they're associated with. They're going to take on the name that comes from the associated 2D graph. And even though that graph changes a bit as you go up in dimensions, it still takes on the name of the 2D graph. And so if you extended this equation to 4 dimensions, x, y, z, and then you added on plus w minus m squared is equal to r squared, you could think about that as the equation of a circle in 4 dimensions or the equation of a sphere in 4 dimensions, however you want to look at it. And if you had a linear equation in 4 variables or 5 variables, you could think about that as a line in 5D or a plane in 5D, however you want to look at it. Okay, next, we want to talk about the slope of a line. The slope of a line. One of the important characteristics of a non-vertical line is that for every 1 unit of change in the horizontal variable, the vertical change is a constant m called the slope of the line. So any line, whether it be in 2D or 3D, or even if you're abstractly thinking about a line in more than 3 dimensions, has a characteristic associated with it called its slope. This isn't a variable quantity associated with the line. This is a constant value associated with any specific line called its slope. Okay, and so if we draw a line in a plane here, okay, what this definition we just read says is that the slope of the line corresponds to, if we start anywhere on the line, wherever we want, let's say here, and we move 1 unit in the horizontal direction, then the amount we need to move in the vertical direction to get back to the line is the slope, m. And the way it works is that you could do this you could choose any point anywhere on the line. The line extends infinitely in both of its directions. You could go to any point on the line and do the same procedure, move 1 unit in the horizontal direction, and then the amount you need to move to get back to the line in that case is going to be this same exact value, m, called the slope of the line. Right? We could come here, move 1 unit in the horizontal direction, then the amount we need to move to get back is going to be that same exact value, m. Okay, but we think about the slope of a line, though, as a ratio. It's a ratio of the amount of vertical movement per horizontal movement. So, okay, in this case, this was 1, and we can see this, the m here was 2. So the m, the slope, is 2 divided by 1. You had 2 units moved in the vertical direction per every 1 unit moved in the horizontal direction. So what you can see is that we could determine the value for the slope of a line using any length horizontal and vertical paths. So, for example, we could start here and then move however many units we want in the horizontal direction. Let's say 3. And now we just go however many units we need in the vertical direction to get back to the line. And that ends up being 1, 2, 3, 4, 5, 6. Okay, and so we could determine the slope by just dividing how many units were moved in the vertical direction per how many were moved in the horizontal direction. 2. Same slope. Okay, now what's interesting to think about, though, is that we can determine the slope of the line not only using any length horizontal and vertical path that we want. So you just divide this length by this length, and you get that same slope m. In this case, it would be 2. But also, the direction of the path we choose doesn't matter. So if we start here, we could go vertical first, and then horizontal. Okay, so we went 1, 2, 3, 4, 5, 6 units vertically, and then 1, 2, 3 units horizontally, but you're still just dividing the amount you moved in the y and x to get back to the line. In general, the way you look at it is, to fully generalize any line, you're dividing the amount you moved in the output by the amount you moved in the input. The slope of a line is always amount of units moved in the output per amount of units moved in the input. Okay, and now, but we also take into account the if we went in the positive or negative y or x directions. So, okay, here we went 6 units in the positive y direction, 3 units in the positive x direction. So the slope is 2, just like what we calculated originally. 3 units in the positive x, 6 units in the positive y. Okay, but notice, though, we could also start at this point and move to this point. So in that case, we would go -3 units in the x and then -6 units in the y. So -6 divided by -3 is still +2. And it makes sense that this line has a positive slope because the general way you think about it is when you move in the positive input direction, does the output change positively or negatively? If it changes positively, then the slope is positive. If it changes negatively, then the slope is negative. Well, in this case, when you move in the positive input or x direction, the output value goes up. It's a positive slope, okay? Now, if we had this line, if we pick any point to start, now let's move 1, 2, 3, 4 units in the horizontal direction, and now we have to move in the -2 units in the negative y direction to get back to the line. So that's 4 and -2. The slope is going to be negative because it's -2 divided by 4, which is -1/2. For every 2 units we moved in the positive x direction, we went -1 unit in the y direction. Or if you look at this per unit of horizontal input, for every 1 unit we moved in the input direction, we went -1/2 of a unit in the output direction, or the y direction. And again, you can perform this calculation in any direction like this, or you could start here and go backwards in any direction. and you're going to get the same exact slope value. Divide the amount you moved in the y direction, positive or negative, by the amount you moved in the x direction, positive or negative, to get back to the line, and you're going to get the same slope value for that line every single time. Okay, so we just saw a method that you can use to calculate the slope of a line. You know, going to any point and then following how many units you go off the line vertically, horizontally, and dividing and getting that ratio. But a more general formula you can use to calculate the slope of any line is called the slope formula. All you need to use the slope formula is the coordinates of 2 points on the line, 2 separate points on any line. If you have the coordinates of 2 separate points on any line, then the slope of that line, m, which in general is the change in y divided by the change in x, right? As you walk along that line, what's the ratio of the change in output per change in input? Okay, so now we've got these 2 points, point 1 and point 2, with coordinates x1, y1, and x2, y2. And what's nice is that which point you pick to be point 1 or point 2 does not matter at all. You can pick whatever point you want in any orientation. Doesn't matter which one's on the left or the right, up or down. You can make any point to be point 1 or point 2. It doesn't matter. And that comes from the fact of what we just demonstrated, in that the directions that you use to calculate the slope don't matter. And so, but the formula is, you take y2 minus y1, the y coordinate of point 2 minus the y coordinate of point 1, and divide that by the x coordinate of point 2 minus the x coordinate of point 1. And that is the slope formula, the formula that you can use to calculate the slope of any line. Okay, and so if we look at these two examples, it wants us to calculate the slope of the line that goes through. So part A, these 2 points. What is the slope of the line that passes through these 2 points? Remember from geometry, if one of the constraints, if you have 2 separate points, that constrains a unique line. So it makes sense that once 2 points, separate points, are specified, that's a unique line with a unique slope. So we can calculate the slope of this line that goes through these 2 points. And we do that with the slope formula. We pick one of these points to be point 1, the other to be point 2. It doesn't matter which is which. So 1, 2, whatever. Okay, so y2, 5, minus y1 is minus 2, so minus y1. Okay, y2 minus, and then y1 is minus 2, over x2 minus, and then x1 is minus 3, x1. Okay, so we've got 5 minus minus 2, so 5 plus 2 over 2 plus 3, that's 7 over 5. That's the slope of this line. You can look at this as, for every 5 units you move in the positive x direction, you have to move 7 units in the positive y direction to get back to the line. Or if we do this per unit, then it's for every 1 unit you move in the positive horizontal direction, x direction, you have to move 7/5 of a unit to get back to the line in the positive y direction. Okay, part B. Let's calculate the slope of the line that goes through these 2 points. Let's pick this to be point 2, this to be point 1. It doesn't matter. So y2, 0, minus y1 over x2 minus x1. So 1, let's write as 2 over 2. So we've got 0 plus 7, okay, minus 5 halves minus 2 over 2, that's minus 7 halves. So this is equal to minus 2. The slope is negative. For every 1 unit you move in the positive horizontal direction, you have to move 2 units in the negative y direction to get back to the line. Okay, now let's think about calculating the slopes of 2 of the special cases of lines in a plane, the horizontal line and the vertical line. So let's calculate the slope of this horizontal line here. The line y is equal to 3. Well, okay, we know that any point on that line is going to have y coordinate 3. So we know one point is going to be 2, 3, and another point is going to be 4, 3. Okay, so now let's use the slope formula. Let's say this is point 1, this is point 2. So y2 minus y1 over x2 minus x1. That's 0 over 2, which is equal to 0. The slope is 0. And this makes sense because for any amount you move in the horizontal direction, you're not going to move any in the vertical direction. There's no slope. So any horizontal line is going to have a slope of equal to 0. Okay? Now what about a vertical line? Let's calculate the slope of the vertical line that goes through x is equal to 2. So the line x is equal to 2 with the equation x is equal to 2. All right, so if we take 2 points on this line, so the x coordinate is going to be 2, and we can use, so 2, 1, and 2, 3. Okay, so let's use this as point 2. This is point 1, so y2 minus y1 over x2 minus x1. So 2 over 0, well, you can't divide by 0. So a vertical line doesn't have a slope. It's undefined. A vertical line has no slope. Now, we can get some intuition behind what the slope of a vertical line is if we think about a line that's just barely tilted off vertical. So if we think about calculating the slope of a line like this, then if we just move a little bit off the line in the x direction, we're going to have to still go a relatively large amount to get back to the line. And so what you have is a large number, like say 50, over a small number, like, something like that. When you divide a large number by a small number, you get that's large number. When it comes to a ratio, dividing two numbers, the larger the numerator and the smaller the denominator, both of those cases make the ratio get bigger. So we can think about a line that's extremely close to vertical as just having a huge positive slope or huge magnitude of slope, because this could be tilted to the left, then it would be a huge negative slope. And so one way we describe the slope of a vertical line is we say the slope is infinity, but infinity is not a number. So technically you can't divide by 0, so the slope of the vertical line is undefined, but we can think about it as just being like infinite. You don't move any in the horizontal direction, and then you could move as much as you possibly want in the vertical direction. Okay, and so with that, we can summarize the general linear equation in two variables. The equation that it's technically not a function. It's just this general equation that is representative of any line in the Cartesian plane. A, B, and C can be any real number. The only restriction is that both A and B can't be 0 at the same time. Then with that, this is the form for any line you could draw in any orientation in the Cartesian plane. And what we saw was that if both A and B are not 0, and C could be whatever, then you're going to have a slanted line, with a line that's slanted in this orientation having a positive slope, and a line being slanted in this orientation having a negative slope. Okay, now if A is equal to 0, and then B can't be 0 in that case, and C is doesn't matter, whatever, then in that case you have a horizontal line. You have y is equal to a constant. It simplifies to y is equal to a constant, and that's a horizontal line, which has a slope of 0, equal to 0. In these slanted cases, you're going to have a non-zero slope. This case, it'll be positive slope. This case, it'll be negative. Here, it's not positive or negative. The slope is 0. Okay, now in the case of when b is equal to 0, which means that you can simplify to x is equal to a constant, that is a vertical line, which has an undefined slope. It doesn't have a slope. Okay, now before we move on to the next section, we can think about how the idea of a slope comes into play with a line in three-dimensional space. All right, so we can start at any point we want on this line. Let's say we start here. Okay, and so now from there, let's walk a certain amount in the y. Let's walk a certain amount in the x, and then whatever amount we need to walk in the z to get back to the line. So in this case, let's say we walked 4 in the x, 2 in the y, and 8 in the z. Well, in this case, the idea is that the proportion of these three values is constant. So we've got 4 in the x to 2 in the y to 8 in the z. So we can simplify this to it's 2 to 1 to 4. This proportion is constant for the entire line. And in the same way, you could walk in any direction you want, going forward or backwards, and you're going to get the same proportion. Okay, now also note that it might get confusing in terms of you're thinking to yourself, okay, well, I need to divide the vertical direction by the horizontal direction to get the slope. But then in some cases, it's like, well, what's the vertical direction? What's the horizontal direction? Here, yeah, I mean, I guess z is the vertical direction, but it's like x and y are the horizontal directions. Like, how does this work? You want to think about it in the sense that it's outputs divided by inputs. It's ratio of the amount of change in output per amount of change in input. So even as we talked about in the previous section, we could think about relations or functions with like these multiple vector inputs, these two or multi-dimensional inputs, kind of like here we input an XY pair, and even multi-dimensional outputs, vector outputs. You know, you input the weight and size of a package, and then what you output is the cost and shipping time. Well, in that case, you're thinking about a slope in the sense of ratio of change in outputs to change in inputs, in whatever context that would come into play. Okay, now, what we want to do next is we have the what I like to call the general form, even though the book calls this the standard form, for the equation of a line in two variables. I like to call this the general form because it's similar to the general form of the equation of a circle. It's just everything expanded out to where you can see the different variables and their powers that you have in this equation. But furthermore, you can't look at this an equation of a line that was something like, and you can't look at this and read off any specific features of the line, similar to in the way that we were able to do with the standard form of the equation of a circle. Here we can clearly see that we have a circle here centered at 2, 5 with radius 4. But just looking at this equation here, we know this is a line, but that's really just visually the only information we can really get from this equation. Again, similar to if we put the equation of this circle into the general form. All we see is just the variables and their powers laid out, which is still useful in some situations. So what we want to do now is we want to create another form for the equation of a line in a plane that's more descriptive, that has information that you can visually see in it pertaining to features of the line. So to create this equation, we can use the slope formula. So again, the slope of a line is the slope formula is you pick 2 points, label one point as point 1, one point as point 2, it doesn't matter which. And then the slope is the y-coordinate of point 2 minus the y-coordinate of point 1 over the x-coordinate of point 2 minus the x-coordinate of point 1. Now, okay, but which 2 points are we going to choose? Well, to create an equation in two variables using this slope formula, one of the points is just going to be, just x, y. We'll say point 2 is just the variables x and y. Because the idea is with this equation, we'll be able to input any x, y point on the line, and it's going to satisfy the equation, right? So, okay. Now, the other point, what we're going to do is, if we think about all of the cases to where we have a slope, which is any line in any orientation except for a vertical line. So if we think about slanted lines or a horizontal line, anywhere in the plane, what you can think about is that any line like this is going to have a y-intercept, 100%. And not just that, but one y-intercept, because these are like a slanted line or a horizontal line is a function, because it passes the vertical line test everywhere, so it can only have one y-intercept. So any line except for a vertical line is going to have a y-intercept, right? And the coordinates of that y-intercept are going to be, so the x-coordinate is going to be 0, and let's say the y-coordinate is b. So, and then the other point is just any point on the line, wherever. So let's plug these 2 points into the slope formula. This will be point 2, this will be point 1. So we've got the slope is equal to y2, which is just y, minus y1, which is b, over x2 minus x1. Okay, so we've got y minus b over x. Okay, now if we multiply both sides by x, we get y minus b is equal to mx. And if we add b to both sides, we get y is equal to mx plus b. And there we go. There's an equation for a line in a plane in 2 variables in a descriptive form, in what's called slope-intercept form. It's descriptive because if we have an equation of a line in this form, then we know that this is the slope of the line and this is the y-intercept. So it's very useful. Now, this can be used to represent any line in the plane except for a vertical line, because a vertical line doesn't have a slope. Okay, very interesting. So now if we look at this example here, if we're given this, what I like to call the general form for the equation of a line, but the textbook calls this the standard form. But then they call the standard form for the equation of a circle that descriptive form, and then they call the more general form the general form. So, but okay, we know we can put this into slope-intercept form, because we know since this coefficient and this coefficient are both non-zero, that this is going to be a slanted line. So we know that it's going to have a slope. So we can put this into slope-intercept form. And to do that, let's solve for y. So let's subtract 3x from both sides. Okay, now let's divide both sides by 4. Okay, so now let's put it in the slope-intercept form. Put the minus 3/4 x first, plus 1. And there it is. There's the slope, and there's the y-intercept. And so we could graph this, let's see, by so okay, y-intercept is at 0, 1. So the line passes through this point, and that makes sense because when x is equal to 0, y is equal to 1. You could plug in x is equal to 0 and see that. Now from here, the slope is, we can go in any direction we want. So we could say for every 4 units you go in the positive x direction, you go down 3 units in the y direction. So we could plot the next point by doing 1, 2, 3, 4. 1, 2, 3 to plot that point. Or we could go in the other direction. So we would say that it's a negative slope. So if we go up 3, so in the positive y direction, 1, 2, 3, then since it's a negative slope, we need to go in the negative x direction 4 units. 1, 2, 3, 4. Okay, so something like that. Okay. Now, what we can do with this slope-intercept form for a line is that, so there's two things you can notice about this form. So y is equal to mx plus b. The first thing you might have noticed is that this form applies for every line that you can draw on the plane except for a vertical line, which what that means is that this applies for any line that acts as a function. Okay, and you could also see that we could look at this as a function because we've got the y by itself over here on one side of the equation, and then the rest is just expressions of x with no pluses or minuses anywhere, which we saw was indicative of a function. So we can use this form to define the linear function. Okay? The linear function is, so we could say y of x or f of x is equal to mx plus b. So if you're ever wanting to model something linearly, if you think that there's a linear relation with, the cost of packages, whatever, you can use the linear function. Because remember, the idea when it comes to functions are as we've talked about, are the most commonly used algebraic model. If you're trying to model something like the cost of a package or the time to do something or whatnot, a vertical line, so the input is x is equal to, or the time is equal to 3 or something, and then the output is like an infinite number of outputs. It's functions. A lot of times, if it's not a function, it doesn't make sense for the application. So, but if you think that there's a linear relation between variables, inputs and outputs, then you can use here's the linear function. You input and you give an input, and you're going to get an output. Now, just to give you a little bit of perspective on why we can't, the vertical line doesn't apply here. Well, one, because again, we saw that we couldn't calculate a slope value with a vertical line, but if we take the general form or the standard form for the equation of a line, well, let's try to put this into slope-intercept form. We subtract ax from both sides. Now divide both sides by b. Okay, is equal to minus a over b x plus c over b. Well, okay, this is fine, except b can't be 0, right? Well, for what cases, when is a vertical line 0? With this general form here, this or standard form, when do we get a vertical line? That's when b is equal to 0, because you get x is equal to a constant, right? A vertical line is like x is equal to minus 3. That's a vertical line. In that case, b is 0, but we can't really put it into this standard or this slope-intercept form to solve for y if b is 0. You see? So that's where why it's a function, the slope-intercept form. Okay, now, but the notation that we use here, this is something that's important to note. This is the linear function. It's like in your algebra tool shed, you can take out the linear function, okay, and you call it the linear function for the cases where you have a slanted line. Okay, but now if you have a horizontal line, in which case m is equal to 0, then you call that the constant function. Instead of calling that the linear function, you call that the constant function. And that's just f of x is equal to a constant. It doesn't matter what x is, it's the same constant, right? It's the horizontal line. And the only reason you want to use this notation is because, you can think about how you might, if you think about these algebraic functions as coming out of your tool shed, you would use the linear function for one application, and you would use the constant function for like a different application. It would be two different scenarios when you're needing to use the constant function versus the linear function. That's the only reason that there's two separate names. But other than that, yes, I mean, they both come from the slope-intercept form. The constant function is just when you have a slope that's equal to 0, is all. Okay, so here's an example where we're given a point and a slope, and we want to go ahead and write the corresponding linear function. So there's some minimum amount of information you need to specify to fully constrain a line. You could give two separate points. If you give two different points, that constrains a unique line. And another criteria would be a point and a slope. If you just provide a point, that's not enough, because you can have a point in the plane. Well, I can draw all kinds of different lines through that point, right? Now, if you just specify a slope, that's not enough, because, okay, I can draw a bunch of lines that it's not a unique line, right? But if you specify 2 points, that's going to, now there's only one line that you can draw through those 2 points. If you specify a point and a slope, now there's only one line I can draw through that point. So, okay, we have a point and a slope. M is equal to -4, and we've got the point 2, -3. So what can we do to find the function, the linear function that corresponds to this line here that has slope -4 and goes through the point 2, -3? Well, okay, let's write out the general form here for the linear function. Okay, well, we've got, let's see, we can plug in this point here. So when you have x is equal to 2, y is equal to -3, so -3 is equal to, and then we've got the slope, which is constant for any x, y. Okay, now x is 2. Okay, so now we have an equation in one variable here. So b minus 8 is equal to -3. b is equal to -3 plus 8 is 5. And there we go. So we've got the slope and we've got the intercept. So the function is y is equal to -4x plus 5.